Hi, and welcome again to my Physics Online video lecture series. In today's video, we're going to be talking about two conditions for a system to be in equilibrium. So far, when we have talked about equilibrium, we have made use of Newton's first law. So Newton's first law basically says that if the sum of forces on an object is equal to 0, then the object will essentially remain at rest if it's already at rest, or remain in motion with a constant velocity if it is in motion with a constant velocity. And we've of course changed this a little bit as we've discussed the idea of linear momentum to say that Newton's first law implies that if there's no net force on an object, then the object will maintain a constant linear momentum. So now let's consider a system. Maybe I have an object like this little board, and I put the board on the edge of a table, like so. So it's on the edge of a table, and we have some normal force acting upward on the board from the table. It actually acts upward at each point of contact between the board and the table. And we also have some weight from the board acting downward everywhere. And that is basically everywhere where there is some mass of this board. Now, it's possible for these two forces to be in equilibrium like this, and yet it's also possible for the board to nevertheless fall off the table. So this tells us that this first condition, Newton's first law, is actually our first condition for equilibrium. It tells us that this is a necessary, though not a sufficient, condition for the board to actually stay on the table at equilibrium. Put differently, there is a second criterion which needs to be taken into account. So our first condition, we had a board sitting on a table, and maybe the board is overbalanced. Like here's a cartoon of one where the board is very much hanging off the table. And if I put a second drawing in which I've just shifted that same board over by several centimeters, so that it's like this, we know that this board right here is likely to fall off, and this one right here stays in place. So stays at rest, or whatever you want to say. So what's the difference between this picture right here, number 1, and this picture right here, number 2? Well, in both cases the forces are balanced, but in the second case, not only are the forces balanced, so that I have a normal force at each basic point on the board where it's in contact with the table, but the forces are balanced in such a way that the torque for the system is also balanced. So put differently, our second condition, our first condition of equilibrium, therefore, is that the forces must all balance. The second condition for equilibrium is that the torques for the system must also balance. So the sum of torques must also equal 0. So those are your two conditions for an object to be in equilibrium. Put differently, it needs to be both in translational equilibrium and rotational equilibrium. So this first condition is the translational equilibrium condition. So we could say this is sufficient for this to be in translational equilibrium. The second one is the rotational equilibrium condition. And so that means that it is at equilibrium with respect to rotations. We will see in a future set of these videos that torques, as I've said before, pertain to the rotational acceleration and the rotational angular momentum, just as forces apply to translational acceleration and translational equilibrium. So let's have kind of like a conceptual question here. Let's say that I have an object, and maybe the object is like this, and I suspend the object. So maybe I happen to have a string located right here to put an upward force on it. Whoops. And maybe I hang a mass from this object so that I have a downward force like this. So maybe there's like a hanging weight attached to the object like this. So I have a force over here. Will this be in equilibrium? Well, it depends. It's possible for some choice of location and some amount of weight here to put this system in equilibrium. Obviously this upward force is longer than what I've drawn it. They're not to scale. We might ask, where should we treat the weight of this object as acting at? And the answer is that there's generally a center of mass and a center of gravity for the object. And that is the location where we might say that the force of gravity on the stick, or whatever this thing is, we can call it a stick, is said to act. So acts at center of gravity. We'll come back to center of gravity later. We've talked about center of mass for a system before. And so this right here would be the force from suspension. And so it's necessarily true that if this is an equilibrium, the suspension force must be equal to the weight of the stick plus the weight of, well, the weights that we've hung from the other end of the stick. So this is the first condition. The second condition says that the torque must be balanced. And for that we have to pick an axis of rotation. So perhaps we pick the end of the stick as our axis of rotation. So this will be my axis. And so this would be, let's say, our stick. We could call this one right here our suspension. So RST, RSU. And then this one right here over to where this point is, this would be RW. And so looking at this, I would basically have R suspension times F suspension must be equal to R stick times the weight of the stick plus R of the hanging weight times F of the hanging weight. Now in a future video we will explore a little bit more about where this axis of rotation might be placed. This actually suffices as an axis of rotation if the system's in equilibrium. If it's not in equilibrium, then there will be a preferential axis of rotation. But if it's in equilibrium, we'll see in a future one that it doesn't matter where we pick our axis of rotation to be. So before we stop for the day, let's do a quick example of finding, let's say, a force and a placement using these conditions for equilibrium. So we have this meter stick, and it's going to be suspended using a string. The axis of rotation will be taken as one end of the meter stick. So this is my axis. This is 50 centimeters from the axis and is the center of mass. The string is presumably placed over here somewhere, but we don't know exactly where. There's going to be some tension force acting upward on this. There is a mass of the stick times G down here. And then over here I have an additional force, which is the extra weight. We'll call that M sub W times G. Okay, so this system somehow has to be balanced. In order for that to occur, the sum of forces must be 0 and the sum of torques must be 0. Sum of forces being 0 implies that the tension force, which is upward, minus the mass of the stick times g minus the mass of the weights times g is 0. And therefore the tension force must be equal to the mass of the stick itself plus the mass from the added weights, whoops, that's mw, times g. And so this force of tension must be 105 grams or 0.105 kilograms plus 0.085 kilograms times 9.8 newtons per kilogram. Therefore, my tension force should be 1.862 newtons. And so if we round that to basically two significant figures, we'd say the force of tension is about 1.9 newtons. Now, the other half of this is to balance the torques. And in some sense, what we can do is figure out which ones are pointing out of the board and which ones are pointing or out of the screen and which are pointing into the screen. So I'm actually going to draw this again, and I'm going to draw it a little bit wider than is normally warranted, because what I want to do is I'm going to kind of color code my forces and where they are. So this right here is my axis of rotation either way. I have on the one hand the weight of the stick, and so this force is the m stick times g. We could call this force stick. And this right here is my r vector. So r is in this direction. Right hand rule says that this is actually a torque. We'll call this torque stick. Direction is into the screen, so that's negative. Now let's do for the string. I don't necessarily know where the string is per se, but I'm just going to treat it as if it's over here somewhere. So this right here is my tension force, and the radius to get to that tension force, this would be r for tension. And the right hand rule says that this is actually out of the board or out of the screen away from us. And then for the last part, I have somewhere over here a hanging weight, and this hanging weight MWG, I'm not necessarily drawing it to scale, so it's not necessarily supposed to be to scale, but here's MWG, and the radius for the hanging weight would be this one right here. And so my right hand rule, R cross MG, remember that this in some ways would extend over here, and so I'm looking at this vector that's greater than 90. It's the 270 degree angle, which means that the sign will be negative, and therefore I should say that the tau from the weight is into the board or negative. So if I put all these things together, what I basically have is R for the tension times F for the tension, which is positive, minus R for the stick times MS times G, where MS is the mass of the stick, and this radius that points to the location of that force is R stick, and then minus RW times MWG should all be 0. And so I can solve this for R tension, basically where am I putting the string, by adding these two terms to both sides. And so I have RS MSG plus RW MWG G divided by the force of tension that I found over here. Alright, I can now plug some numbers in to my equation to get the location that the string must be attached, that the tension must be applied at. So stick was 50 centimeters, mass of stick was 105 grams, which is 0.105 kilograms. To that I have to add the 90 centimeter for the weights times the 0.085 kilogram mass for the weights, and then all of that has to be times 9.8 newtons per kilogram, and then we have to divide that by, again, this tension force that we found, and I'm actually just going to use this longer term since it's already in the calculator, 1.862 newtons. Plug everything into the calculator, and what do we get? We get that the location of this string should be 67.8947 centimeters from the end that we designated as the axis of rotation, or if we round to the two significant figures that this thing warrants, about 68 centimeters from the end. So that is a reasonably straightforward example because you've been given all of the forces but one, and all the locations but the same forces location, and you've been told where's the axis of rotation. So that's all for today's video. Thanks for watching. Hopefully you've learned a bit from the time you've spent on this video. See you in the next one.